In this video, I'm going to be talking about what an inverse function is to help you do your 12.2 homework. I will do 12.2 homework examples in separate videos. So, before we talk about an inverse function, let's remember what a function is. A function is a rule, it's a mapping, that sends each x value to exactly one y value. We don't care where things go, we care that they go to one place. All right? We can represent functions a lot of different ways. Let's review that. Functions can be represented many ways. What do we have? We have just ordered pairs. So for an example, here's a function that sends 2 to 5, and it sends 6 also to 5. The domain is just 2 and 6. 2 is just sent to 5. 2 is not sent anywhere else. 6 also happens to be sent to 5, but 6 is only sent to one place, so this thing is a function. You can also use a mapping diagram to show this data. How about we just number these? So for an example, here's your domain. We'll just use that same function. Here's my range. So we are sending 2 to 5, and 6 is also being sent to 5. 2 is going to 5. 6 is also going to 5. This is another way to show the reader this function, this mapping. You can also graph the ordered pairs. Right? 3, we could represent it by graphing. And we can do this one, but I want to do another one that's continuous. 2 to 5 and 6 to 5 as well. Just do a little quick sketch. 2 is going to 1, 2, 3, 4, 5, and so is 6. All right. So I could just show the reader those two ordered pairs. It's showing me that 2 is going to 5. It's showing me that 6 is also going to 5. That one's not terribly interesting, but we can also have, just to review, like a function that was continuous. How about this graph? And I'm just going to name it y equals f of x. This is still a function. If you recall, if you fix an x value, say x is 1, and I draw a vertical line so I can imagine all x values that are 1, that should go like right through the 1. The fact that there's only one intersection means that 1 was only sent one place. And I don't care where it goes. Maybe we send it to 3. but I care that it goes to just one place. So the way that you can quickly see if you have a function is if you imagine a whole bunch of vertical lines and you confirm that they're intersecting that graph only one place. Vertical line test. Right? But if you have a graph that fails the vertical line test, like this, for an example, how about right here? You see that we've got more than one intersection, right? This fails. This is not a function. Okay? Just moved that over so it fit. All right, and then the fourth way that you can show the reader a function is with a formula. Right, and we've got some examples, like our lines. I wrote a y because I was already on this. Y equals, say, 2x minus 1. This is a function. You could go ahead and graph that line and see that it passes the vertical line test, but imagine putting in a number for x, any number, then on your calculator, multiply it by 2 and then subtract 1. Is your calculator going to spit out more than one answer? No, it's going to spit out just one y value. This is a function. This is also a function. We've been studying quadratics. Y equals, say, minus 3x squared plus 2x minus 5. This is also a function. Imagine on your calculator, pick any number, square it, multiply it by itself, then multiply it by 3, then add twice that number, and then subtract 5. Your calculator's not going to go, oh, well, it could be this answer or that answer. No, it's just going to spit out one number. It's going to spit out one y value. So I've reviewed what a function is and our different representations of showing the reader a function, because now we're going to talk about inverse functions. We're going to talk about going backwards. And because you can represent functions with 4 different ways, ordered pairs, these mapping diagrams, graphing, or with a formula, you can come up with inverse functions in those 4 different modalities. Okay, so now let's discuss what an inverse function is. An inverse function, is a reverse mapping. What do I mean by that? So, for an example, say the function f, we're describing it with these ordered pairs. 2 is sent to 7, 3 is sent to 6, and let's be playful, 0 is sent to pi. 2 is going to just one place, 7. 3 is going to just one place, 6. And 0 is going to just one place, pi. All right? Then the inverse function we denote that with an f with a little tiny minus 1 up there. I know that's a little confusing because we're used to that notation being there for reciprocal, but when it's partnered, remember that f isn't a variable, that f, and maybe you guys want me to write the of x. I'll bet you do. Let's do that. So here's my function. F of x is these ordered pairs. The inverse function, we denote F inverse. The reason why we still want to have the F there is to underscore the relationship that this function has with that one. They do and undo each other. Okay, so here's your F inverse, right? If 2 is sent to 7, then F inverse is going to send 7 back to 2. In fact, let's give it a new color. All right, so I'm going to be using this blue for the inverse. So if F sent 2 to 7, then F inverse is going to send 7 back to 2. I'm just going to switch these ordered pairs. If F sent 3 to 6, then F inverse will send 6 back to 3. I'm literally just switching all of the ordered pairs. If F sent 0 to pi, F inverse will send pi back to 0. And there we have it. Given a function with ordered pairs, all you do to come up with the inverse function is you switch those ordered pairs. All right. Now I want to do another example. And maybe this time, instead of showing ordered pairs, I'll do a diagram. So here's my function, f. We're going to write its domain. And its range. Okay. So say this function f sends -3, and sometimes they'll just write the f right above the little arrow so that you see this is the rule for f. We're going to send -3 to 6. We're going to send 2 to 6 as well, how about? And we'll send 5 to 8. All right? Is this a function? It sure is. -3 is only going one place. It's going to 6. 2 is going only one place. It happens to be going to 6, but it's only going to one place. 5 is going only to 8. This thing is a function. But now I want you to think about the inverse and if it exists or not. All right, so we literally switch all the ordered pairs. That means we literally switch the domain and the range. So my domain, if F inverse exists, will just be 6 and 8. And my range would be -3, 2, and 5. Right? If F sent -3 to 6, if I was going to go backwards, I would send 6 to -3. If 2 was sent to 6, if I were to go backwards, 6 would also have to go to 2. This is not a function. This part's okay. 5 going to 8. Well, then going backwards, 8 would go back to 5. That's okay. But this is not a function. Right? I can't send one x value to 2 different y values. This is not a function. So there's no undoing a function like this. So my point is f is a function, but what? But f, or how about this? That does not have an inverse. There's no f inverse for that guy. Okay? Now, graphing, if you were given a function and it's those sets of ordered pairs, how about we do a graphing one with a formula too? How about, here's my function, y equals 1/2 x plus 1. When x is 0, y is 1. We see there's our slope here of up 1 to the right 2. So this is 2, this is 2. Go up 1 to the right 2. Or equivalently, down 1 to the left 2. How about one more? Down 1, we're at -1 to the left 2. Here at -4. Beautiful. This is a function. It passes the vertical line test. And this function is invertible. If you're asked to graph the inverse function, we're literally just going to switch the ordered pairs, right? So since 4 was sent to 3, when we're graphing f inverse, we're literally going to switch them, those ordered pairs. And let's do it. All right, so since 4 is sent to 3, when I switch these, 3 will be sent to 4. Here we have 3, 4. That is a point on f inverse. Since f sends 2 to 2, right? 2 is sent to 2. Well, switching them, we still are at 2, 2. 2, 2. Maybe I'll label them. Okay? Since f sends 0 to 1, switching them, 1 is going to go to 0. There I'm at x is 1, y is 0. Since f sends, last one, actually there's 2 in here. -2 is sent to 0. Then 0 is going to be sent to -2. Lastly, this ordered pair right here is telling me that -4 is sent to -1. -4 sent to -1. So going backwards, -1 will be sent to -4. There we are at -4. All right. Okay, we can talk a lot more about inverses. Like, I would like to know what the rule for this is algebraically, and we will be able to go ahead and find that, but I want to do that in a separate video. I hope we've laid the foundational idea for what an inverse function is. It's a reverse mapping. And not all functions, like we saw here, can have reverse mappings, right? Because if I switch 6 going back to 3 and to 2, look at that. That's not a function. Okay? Thank you for watching.